A shadow is currently crawling across the northern hemisphere of Saturn. As the planet tilts away from the Sun, the upper half of this giant world is plunging into a darkness that will last for a decade and a half, hiding some of the solar system's most complex weather systems from every telescope we possess. Knowing this observation window was closing, NASA released a set of images on March 25, 2026. Captured by the James Webb and Hubble Space Telescopes, this data serves as a final, high-resolution portrait of the northern pole before it vanishes. To understand exactly what we are losing sight of, we have to recognize that the serene golden sphere we are used to seeing in textbooks is largely a trick of the light. We can see this trick in action by looking at the data gathered in August 2024 by the Hubble Space Telescope, as part of a long-running tracking project called the Outer Planet Atmospheres Legacy Program. This is the Saturn you likely recognize. It features smooth, pale gold atmospheric bands, perfectly tilted rings catching the sunlight, and tiny specks of white orbiting the perimeter, moons like Mimas and Janus casting small shadows onto the clouds below. This familiar perspective relies entirely on visible light, the exact same wavelengths human eyes detect. And visible light only reflects off the absolute highest layer of chemical haze. It acts like an opaque ceiling over the planet, blocking everything underneath. Because we rely so heavily on what we can see, it is easy to assume Saturn is a quiet, glittering jewel. In reality, that golden surface hides continuous, continent-sized storms and violent fluid dynamics playing out hundreds of miles below. We finally broke through that ceiling 3 months later, using the massive gold-plated mirrors of the James Webb Space Telescope. Webb captures infrared light. Through its sensors, the pale yellow disappears, replaced by thick bands of deep amber. The rings, made almost entirely of highly reflective water ice, suddenly blaze neon white against the blackness of space. This diagram illustrates how the two telescopes differ. The visible light that Hubble detects bounces right off the flat, uppermost cloud layer. Infrared light from Webb has a longer wavelength, allowing it to penetrate that hazy surface and reach the dense, turbulent atmospheric layers where the weather systems actually form. By taking the surface map drawn by Hubble and combining it with the deep penetrating infrared data from Webb, researchers can cut a vertical slice right through Saturn. We can trace a storm from the deep cloud layers where it originates, all the way up to the thin haze at the top. This combination turns a flat, two-dimensional picture into a living laboratory for fluid dynamics, mapping exactly how pressure and temperature interact in 3 dimensions. The immediate result of this deep scan is a series of structural anomalies. The most striking is at the poles, which emit a distinct gray-green glow in the infrared spectrum. Researchers suspect this specific wavelength of light points to one of 2 things: either an unidentified layer of aerosols scattered high in the atmosphere, or faint auroras generated by charged particles crashing into Saturn's magnetic field. Moving south into the northern mid-latitudes, the data reveals a meandering jet stream called the ribbon wave. Hidden by the visible clouds, this massive current of wind cuts a jagged path through the deeper atmosphere. Just beneath that wave sits a persistent dark spot. This is the lingering remnant of the Great Springtime Storm, a tempest from 2010 that wrapped entirely around the planet. Even over a decade later, the physical scar remains embedded in the lower atmosphere. Yet, just as we finally acquire the tools to track these 3-dimensional structures, orbital mechanics are forcing a shutdown of the entire observation area. While Earth completes a rapid orbit in 12 months, Saturn takes 29 years. Because the planet is tilted, this long journey stretches its seasons. Each pole spends roughly 15 years in continuous sunlight, followed by 15 years in complete darkness. Right now, the northern hemisphere is crossing the terminator line into its long winter. That means the northern pole, along with the massive geometric hexagon-shaped jet stream first discovered by the Voyager spacecraft in 1981, is slipping into the shadows. Once the sun sets fully on this region, the ribbon wave, the polar glow, and the hexagon will become entirely invisible to both Earth and space-based telescopes. We will not see them again until the 2040s. These images from Hubble and Webb serve as a final, urgent portrait of a complex atmospheric ecosystem before it is packed away for the winter. We can build the most sensitive infrared arrays and launch them millions of miles from Earth to pierce through the clouds of a distant world. But the geometry of the solar system still sets the schedule, and it tells us exactly when it is time to turn off the lights.